I've had the great opportunity to talk, for example, with the second most important person in the European Space Agency, Frank Salzgeber. And Frank Salzgeber told me that we don't have to, and we don't need to, and we should not be afraid about crazy ideas. That about in the space industry and startups, that we should go on and try it. Also, for example, the highest, not with it, in the measures of, the height, but in the importance, the Josef Asbacher, the most important person, the Director General of the European Space Agency, told me basically the same stuff. And it is that if we had, for example, the capabilities to travel to America 500 years ago, why wouldn't we do it? So these are like maybe a little bit crazy ideas, maybe some breakthrough ideas. But about breakthrough ideas, we will talk today with our great guest, and it is Pete Worden. Hello, Pete.
Hello.
We are here live right now on the Czech Space portal on Facebook. In Czech, it's Český kosmický portal. And Pete will have some speak today about the great project about traveling with the light sails to Proxima Centauri, our closest star. So we will get know more about this. All this is organized during the Czech Space Week, organized with the Ministry of Transport and Agency of Czech Invest Agency, apologies, and with the other industry and scientific partners. So today, the Czech Space Week will be highlighted with your speech, and I'm really looking forward. And then we'll have some discussions. So if you're right now on the Czech Space portal Facebook, you can pose the questions to Pete, and we will discuss about it afterwards.
Thank you.
Welcome. The floor is yours.
Thank you. Well, what I'd like to discuss today is longer-term efforts that kind of pick up where some of the space agencies let off. I run the Breakthrough Initiatives, which is a privately funded program, which is part of the Breakthrough Prize Foundation, which I also chair. And just by way of background, the Breakthrough Prize is the world's largest science prizes. We give out $3 million US prizes each year. They're actually the largest prizes in science. They're about 3 times the size of a Swedish prize I'm not supposed to mention. But we normally had a ceremony, but for the last 2 years we've had to postpone it due to COVID. We also have a prize for early careers, and we're looking at more, and we have another prize I'll talk about in a minute. The prize ceremony is normally held at the campus of NASA's Ames Research Center. I used to be the director at NASA Ames, and so the ceremonies were started about 10 years ago. They are actually called the Oscars of Science, and they're the idea of our sponsors, and the sponsors consist of some of the biggest names in Silicon Valley and elsewhere, and in tech industry, including billionaires in the US and China, that what we would like to do is inspire young people to go into science. And we really think that scientists should have the same admiration and position in society, maybe better than sports heroes or other kinds of people that are famous. So the prize is the effort to try to do that. I want to just highlight one of the prizes we gave a few years ago. This is Jocelyn Bell Burnell. Professor Burnell is a very noted British astrophysicist. But interesting thing about Professor Burnell is in the 1960s, she was a graduate student at Cambridge University, and she noticed some very strange signals in the radio telescopes that they had there at the university, and they seemed to be very regular. Every second or so there was a beat, and in fact she initially thought it might be aliens, and she called it LGM, for Little Green Men 1. Her advisors told her to ignore it, but she kept doing research, and she was able to show that this actually came from an object in space. It turned out it was a pulsar, the first pulsar, and which is the remnant of a supernova explosion that happened thousands of years ago. The interesting thing is that this was one of the most major discoveries in astronomy in the last 60, 80 years. Her advisors received the Nobel Prize for it, but she was not given the prize. And our committee felt that this needed to be remedied, so she was given a special breakthrough prize in fundamental physics. She took the $3 million and she put it in a special fund for underserved people, including women in science. So really, we're very proud of Jocelyn Bell Burnell being one of our recipients. Now, before I go on to talk about the main topic today, I want to mention another prize we started about 10 years ago. This is the Breakthrough Junior Challenge, and this is a prize that's for young people between the ages of 13 and 18. We ask these young people to do a few-minute video on some science principle in physics, mathematics, or life sciences. The winner gets a $250,000 US dollar scholarship to go any place in the planet. Their school gets a laboratory that has been constructed by the Cold Spring Laboratory in the United States. And maybe the most important thing is we give the teacher that inspired the student a $50,000 check, so to recognize that not only students' work, but the teacher's inspiration. Well, let me now talk about the main topic here. The breakthrough initiatives were started on July 20th, 2015 at the Royal Society in London. Our principal sponsor is Israeli investor Yuri Milner. You can see him on the stage there. He's also a physicist himself. But you also see Professor Stephen Hawking on the stage. Until he passed away several years ago, Professor Hawking was our senior science advisor, a truly inspirational and brilliant man, and we're very proud to have him have been involved in our initiatives. Well, the initiatives are really some of the big questions, and these are very significant questions that I don't have an answer to, but we sure hope to find out, and I'll talk to you about some progress on these. The first one is there intelligent life elsewhere? And now this always raises the question, is there intelligent life on Earth? And my answer is, well, the closer I get to some national capital, usually not. But we are looking for evidence of an intelligence somewhere else in the universe. And we think that this intelligence would reveal itself by what we call a technosignature, indicating something about their technology that could be seen at very great distances. It could be a signal, it could be an indirect piece of evidence, it could be evidence of a giant structure, a lot of different possibilities. This used to be called SETI, the Search for Extraterrestrial Intelligence, and I'll talk to you about this program in a minute, and some rather tantalizing results we had from last year. The second question, of course, is there any life elsewhere? And just to remind everybody, today we know of no other place other than Earth where there's life. I mean, there are those that suspect that there's life perhaps on Mars or other places in our solar system and maybe elsewhere. The third question, and this is to me probably the most exciting, is can we travel to other stars? And to remind you, this is a very difficult problem. The nearest star system, which I'm going to talk quite a little bit about, the Alpha Centauri system, is 4.3 light years away. And just to put that in context, that's 300,000 times further away than our sun. At the speeds we go today, it would take almost 100,000 years to get to the nearest star system. So the question is, can we go faster? Can we get there maybe sometime later this century? Well, the first program we started it was actually announced on July 20th, 2015 as Breakthrough Listen. This is a $100 million US effort funded by Mr. Milner to see if we can find evidence of an alien technosignature. We have time on many of the world's large radio telescopes and optical telescopes around the world to look for evidence of a technosignature. It's actually managed for us by a rather large research group at the University of California at Berkeley. And just to give you, this isn't a complete list, but these are the instruments around the world and actually now in space that we're using to look for technosignatures. There's a couple in particular I'd like to highlight. Right in the center is the Transiting Exoplanet Survey satellite launched about 3 years ago. This was specifically designed to look for planets like the Earth orbiting a nearby star that they would call transit. It means they go in front of the surface of the star, and we can see a dip in the light. It's now discovered dozens of planets, many of them the size of the Earth, and some of them with conditions that could be conducive to life as we know it. This is called the habitable zone. We are working in concert with them. When they find one of these planets, we then point our various radio and optical instruments at it to see if we can see evidence of a technosignature. Two of the instruments that I want to mention on this, one is on the upper right hand, you'll see an array of telescopes. These are, this is the Meerkat Array in South Africa. We have a major program with the South Africans. There's 64 of these antennas. Eventually there'll be thousands of them in something called the Square Kilometer Array. And this will eventually be the most capable and sophisticated and flexible radio telescope in the world. The other one on the bottom in the lower left is you'll see a large single dish. This is the Chinese 500-meter radio telescope, by now the world's largest radio telescope, which we've just begun in concert with the Chinese experts looking for technosignatures. Now, I want to highlight this instrument particularly. This is the Parkes radio telescope in New South Wales in Australia. It's a 64-meter radio telescope. This was actually built in the early 1960s. It's a very famous radio telescope because during the Apollo moonwalk in 1969, it was the radio receiver that received the moonwalk images. So it's been around for a long time and done really great work. Well, I want to put this picture up, and this is a technical picture, but this was quite exciting. Just a little over a year ago, I received a call from the principal investigator of this program at UC Berkeley, and he said, we have our first potential alien signal. And it was called, we named it Breakthrough Listen Candidate 1. And the interesting thing is this signal came from the nearest star. I'll talk a little bit about the nearest star system. It actually consists of 3 stars, but one of them is a little closer than the other 2. It's called Proxima Centauri. We now know, and I'll tell you a little bit more about this, that indirectly we know it has a planet like the Earth in the habitable zone. So it was quite exciting. The signal is that sort of in the center, you'll see a kind of a light yellow streak. The red streak is a calibration streak. This had all the features we would look for with an alien signal. It drifted relative to the Earth in frequency, which meant it was outside the Earth. It was very narrow band. It was a very tight band signal, which would be what we'd expect from an intelligent signal. Natural sources have very broad band. And we were very excited. This occurred for a few hours. We saw from Proxima Centauri a few days before and after similar signals. So we were quite excited, and we started to look in detail at this signal. What could we tell from it? And I might add that the data was taken 1.5 years before this discovery. The discovery was actually made by an undergraduate student at a college in the United States, and very exciting that he finally got around to looking at the data. We then did a lot of analysis, and I might mention that about halfway through the analysis, somebody leaked it, so we had a lot of excitement in the press that we might have found an alien signal. We are now virtually certain that it's not a real alien signal. We think it was terrestrial interference. We still won't know exactly what the interference is, so there's still a tiny possibility that it's from Proxima Centauri, and we're looking very closely at it. But this is the first time we had a method that we really were able to show that might work to find technosignatures. So we're continuing to look at this, and hopefully we'll find some more signals. Now, I want to talk mostly about Alpha Centauri system, and can we go there? The Alpha Centauri system actually consists of 3 suns. It's in the southern hemisphere. If you go south of the equator and you look in the southern sky from there, the second brightest star in the sky is Alpha Centauri. As I said, it's about 300,000 times further away than the sun. And it has 3 stars. One of them is a little bigger than the sun. One of them is a little smaller. They orbit around each other in about an 80-year period. So if we were sitting here orbiting Alpha Centauri A, we would see about where the orbit of between Uranus and Neptune, we'd see a very bright sun. It would be, you know, it wouldn't get much heat from it, but it would be very bright. It would be thousands of times brighter than the moon in the night sky. In the very great distance, you would see a third star that is a red dwarf star, and a red dwarf star is about a tenth the mass of the sun, and it only has about a 10,000th of the light. But it turns out they're very common. There are 70% of the stars in the galaxy are red dwarf stars. Now, we set up a program to see if we could find planets, hopefully a life-bearing planet in the Alpha Centauri system. And at the time we started this, we knew of no planets in this system. But then about 6 months after we started this in 2016, I got a call from the European Southern Observatory, which is based in Munich, and they said that they have detected indirectly a planet orbiting Proxima Centauri that appears to be Earth-size, and it appears to be in the habitable zone, which has now been called Proxima b. Now, this is an artist's conception of what Proxima b looks like, so I suppose we don't need to go there because the artist already knows what it looks like. We know nothing about the planet itself other than its mass is about what the Earth is, and the temperature on the surface would be about what the temperature on the Earth is. But again, very exciting results. But we then agreed with the European Southern Observatory to build a new instrument, an instrument that we could look very precisely, not at Proxima Centauri, but on the 2 bigger stars, and actually see if we could directly image a planet the size of the Earth orbiting one of those stars. And we had 100 hours of time on this array of telescopes. This is the very large array in Chile that's run by the European Southern Observatory. Now, I have to pause for a moment. I'm kind of embarrassed as an astronomer that we aren't very good at naming things, because this is called the Very Large Telescope. And the European Southern Observatory is now building an even bigger one. These are about 8 meters in diameter. It's about 39 meters, and they're calling it the Extremely Large Telescope. And initially they were going to build an even bigger one that was going to be about twice that size, that was called the Overwhelmingly Large Telescope. So if as an astronomer, we need some help in naming things. But at any rate, we had 100 hours of time on this. Now, I put this picture up because probably some of you, like me, are science fiction enthusiasts. And you might recognize this is a picture from the movie Avatar, which was in 2009, was a science fiction movie that was produced and directed by James Cameron. And it featured in it a voyage, a trip where humans are going to the Alpha Centauri system. In fact, that orbiting Alpha Centauri A, the biggest star in the system, is a giant planet, a planet about the size of Neptune, that's in the habitable zone. Now, in the movie, the planet has moons, one of which is almost the size of the Earth, which they named Pandora, that's not only inhabitable, it's inhabited by interesting aliens. Now, when we finished our 100 hours of data, we think we have found a giant planet in the habitable zone of Alpha Centauri A. Very exciting. And it was so exciting that we got a hold of James Cameron. This was in April at our annual conference this year done online. He spent about an hour with us. You can see him on the right center pane there, talking about the Avatar movie. and and what they had thought, how they were going to send probes there. Interestingly enough, the way that the human starship would go to Alpha Centauri would be a combination of what we're going to try to use and fusion propulsion, which I think is coming along quite well. So very exciting. This is online. If you go to the Breakthrough Discuss conference website, you can listen to his very exciting discussion of the movie. He was busy filming the Avatar 2, 3, and 4. He told us. But now let's talk about going there. And in 2016, we started another program called Breakthrough Starshot, which the objective was, can we actually send a probe to Alpha Centauri that can get there in some reasonable amount of time? As you recall, as I said, it might take 100,000 years to go there at the speeds we can go today. And so we had a lot of studies and analysis how we could do this. And we actually had an announcement at the New World Trade Center on April 12th, 2016 of this program. This was Stephen Hawking's last trip to the United States, and along with other experts that helped announce a Breakthrough Starshot. But the idea is figuring out some way to go 1,000 times faster than we can go today, basically 20% the speed of light. And just to put this in context, this is difficult, but we did this in the middle of the 20th century. We increased the speed about a factor of 1,000, so we now can go around our solar system. We have another factor of 1,000 to go to Alpha Centauri. And so we had a study team that looked at this, and their first reaction was like, this is impossible. And but there are some very clever people, and somebody pointed out that this actually, it seems that there are ways to do this, and we'll talk a little bit about what they are. There's a very old idea, and actually in 1610, Johannes Kepler sent a letter to Galileo that said we should sail on heavenly winds in space, and it turns out that there might be a way to do that. It's to use light sails, and we think if we can make a very, very small spacecraft, and I'll talk a little bit about how small, a few grams, and use a very, very powerful laser that, so the laser light is the wind, that we think we can build a light sail that can travel at 20% the speed of light and get to the nearest star system in some 20 years. Now, light sailing is beginning to be quite promising. There was actually a private effort done about a decade ago by the Planetary Society. Since then, the Japanese Space Agency has used light sailing where the sun pushes a light sail. Now, the trouble is the sunlight isn't really powerful enough to get us to these high speeds, but lasers are. The technology to build very, very small spacecraft is coming along quite well. If you have an electronic watch, it has a chip in it. That chip has got all the capabilities of a spacecraft, and so we think that this is quite possible. Now, this gentleman is Professor Zach Manchester, who's actually here in Prague this week for a set of meetings we had with the experts here, and he showed a decade ago that you could build a ChipSat, and he's since launched literally hundreds of these things. These ChipSats are actually built by students, and it's very exciting that what we can do with these very, very small spacecraft. However, the laser itself has to be incredibly powerful. It's hundreds of gigawatts. It's kilometers in scale. This is an artist's conception of what one of these arrays might look like. Now, as you recall, I mentioned that Alpha Centauri is in the southern hemisphere. We would like to have, this is called the photon engine, we'd like to have it based someplace very high altitude, very dry conditions, and those conditions exist in the Andes, the high Andes, particularly the Atacama Desert in Chile. So when we made our announcement here about 6 years ago, some of the press asked me, well, where would we put this array? And I said, well, in Chile. And unfortunately, I forgot to tell the Chilean government So I was summoned to talk with, I've now spoken to 2 presidents of Chile. Fortunately, both of them were very nice, and they said they want to help, but they said, next time tell us before you're going to put things in our country. But one of the pieces of research is how do we build this laser photon engine affordably, and we mean affordably about $10 million or euros. The photon engine itself, this is a picture of what it would look like firing. Now, we showed this picture to our sponsor, Yuri Milner, who's a physicist, and he said, well, this picture is wrong. I said, well, why is it wrong? He said, well, you're going to use infrared light for this laser, and you wouldn't see it. And now, being quick on my feet, I said, well, it turns out you might heat the dust in the atmosphere enough it would glow. And he said, okay, but next time fix it so it looks like it really would. But this is an example of what it would look like firing. Now, it fires for a few tens of minutes, and it goes against a light sail. The light sail is about 10 meters in diameter. We had some discussions this week here in Prague about the technology. This is the second major challenge: is how do we get a material that can take hundreds of gigawatts without falling apart. We have a major program that's being managed for us at the California Institute of Technology. It's made great progress, so we think the light sails are well in hand. And then, go back here. You know, 20, 25 years later, these light sails would fly by, say, a planet in the Proxima Centauri or Alpha Centauri system that take images and maybe other data and then beam that back on a small laser beam to Earth. That's the third major challenge, is how do we get enough power and point this laser beam back on the Earth. We have a program we've just started on that to do the basic research. I might add we're going to send thousands of these light sails. We call them nanocraft. Now this is a picture from National Geographic. It's not really accurate because they don't all arrive at once. They arrive every few days later. But it is accurate that the light sails would have little holes in them because in interstellar space there's pieces of dust. So we would have some of those dust would poke holes. Some of it might hit a vital part of the light sail and destroy it. That's why we'd send a lot of them. Now, I always get asked the question, well, these are just small robots. Can we humans go to Alpha Centauri? And I don't know, but I'm optimistic. There's another foundation that we work closely with called the Limitless Space Institute in Texas. And they are funding a number of efforts that are more speculative, including things that work like, you know, starships you see in the movie that maybe make wormholes they go through, or warp drives. But one of the things that is less speculative is fusion propulsion. And it turns out that a fusion propulsion looks to be quite feasible, where it would have, you know, thousands of times better performance than our best engines today. There's a company in California called Helicity Space, which is starting to develop these engines. Interestingly enough, as I mentioned, James Cameron said when they postulated a decade ago, they would use two things. They'd use a laser to push it really fast, and then at the other end, they would use fusion to stop. So the question is, maybe next century we could actually send bigger payloads and even humans. Now, we have a last program that we're starting to look at is, can we do private missions to places in our own solar system? There's at least 5 that we think could have life. Probably microbial life. There's no evidence of anything, well, there's no evidence of any life yet. But one of those is Mars. There's a lot of missions to Mars. Other places in the outer solar system are what are called ice worlds. These are things that are moon-sized, the size of our moon, or maybe a little smaller or bigger, that have a frozen surface underneath which is an ocean. At the bottom of the ocean, there's a rocky core of the moon that actually has volcanoes that is heating the ocean and can produce evidence of or possibilities of life. But my favorite place to look, this is Earth's evil twin, Venus. The surface of Venus is 500 degrees centigrade, so any sort of life we know is unlikely to be there. But there's a level in the atmosphere of Venus, about 50 kilometers above the surface, that there seems to be temperature and pressure about what it is here in this room. It's right in the middle of Venus's clouds. The planet is covered with clouds. The clouds are actually made of sulfuric acid, but there's some ideas that life could exist there. And it turns out about a year and a half ago, there was evidence of a molecule called phosphine. It's a poison gas, but on Earth it's almost always associated with life, and it may be that Venus has life on the surface. There is a mission that's likely to go to Venus that's privately funded by Rocket Lab, a company in Australia, or I mean New Zealand, and we're looking at maybe putting an instrument on it to look for life. So if all goes well, here later this century, we may have our first evidence of life, on the nearby star system, and further after that, we can go there. Well, let me stop there, and I'll be happy to answer any questions. Thank you.
Yeah. So let's have a telescope called Pete, right?
Yeah, well, we should name it Breakthrough.
Breakthrough, okay, Breakthrough. And the extremely large will be?
Yeah, that's Milner.
Milner, yeah. Okay, why not? Let's go. How far are we? How far are we in this project with the light sails? When do you? Okay, I've heard your interview. It's like 2 years ago.
Right.
So, what's the progress?
Well, I think with most technological things, you go both faster and slower than you imagine. I'd say in some of the areas we're much further along than we thought. We originally thought that the light sail was going to be the hardest part, but we've had a number of breakthroughs in the light sail, and we're now quite confident that light sails can be built. It turns out we have to have 10 meters. We can build, kind of a few millimeters, but that's an engineering challenge, which tends to be solvable. The second question is the laser itself. We did have a major breakthrough that was done by the Australian National University, and they showed that one of the big problems is if you have lasers covering several kilometers, that you need to have the laser on this end and on this end. They need to fire in concert. It's called, they need to be in phase. And they showed a way you can do that, and that was a major breakthrough. Now, our biggest challenge with a laser is, can we build this affordably? And there are a couple breakthroughs in laser technology that we think will get us that. We'd like to build this thing for a few tens of millions of dollars, and those look quite promising. To me, the hardest problem is going to be getting the signal back. This is the communications. And we've just started this research, and I think it's doable, but it seems the biggest challenge is getting enough power. Because even in a few grams, we can put a fairly powerful laser, but you have to find enough electrical power to power it. And we're just beginning to look at that. So that's going to be a challenge. Sometime in the next year or two, we're looking at maybe doing some experiments in space where you begin to start showing this is feasible. So, I would say by, 15, 20 years, you'll start to have prototypes. There are other things that are coming along that much sooner. The light sails are so promising that there's a group in California funded largely by NASA that thinks in a few years you can build what's called a sun diver. That you build this light sail, it's actually quite small, it's a few kilograms. It dives in towards the sun, deploys its sail, and then you're close enough to the sun that you can get speeds, now not fast enough to get interstellar, but get to the outer solar system rather than a few decades in a few years. And so there's breakthroughs that are coming along pretty regularly. I mentioned fusion. We think those fusion engines might be working by the end of the decade. Now, it's a long way before you make an interstellar fusion drive, but I'm again a science fiction enthusiast, and there's a TV show called The Expanse. Maybe a lot of you watched, and this is, I don't know, a few hundred years in the future, and it shows that humanity is throughout the solar system, but they're throughout the solar system based on fusion propulsion. So these things are coming along, I think, better than I expected.
If you're thinking you are doing moonshots at your business, so maybe get down with it.
Star shots.
Star shots, yeah. 2 years ago, also with that interview, I've heard that you were not decided already about if those chips will be maybe on that sail itself, like cover the whole sail. So do we have any progress with these decisions?
Very much so. We are convinced now that we'll have to distribute the sail material. So the whole sail will be the spacecraft. So it's not just a little chip in it. And beginning to be looking how to do that. And so that rather than have this sail with this little chip embedded in it, one of the problems is if you start to accelerate it, if it accelerates slightly differently, the chip will tear out. So we think it'll be distributed across the entire sail, and we're beginning to look at the design. Some of these experiments we look at would probably have that.
Basically, those sails, these spacecrafts, will not stop. They will not get back. They will travel through the universe forever. Are we basically will we scatter basically the information about the intelligent civilization through the whole galaxy like that?
Well, it's, yes.
Is it one of the points why are we doing this?
Well, it turns out that one of the big arguments you're getting at is the question of communicating with aliens, and that's quite a controversial area, and we choose not to get too much arguing in that. The argument is that if I send probes out, then we've announced ourselves. If somebody can find those, of course, the technology to find a tiny chip or even a few meters in diameter sail in the vastness of space is pretty hard. If they can find that, they can find us without having to find the sail. So I think I wouldn't worry about that. But one of the more interesting things, and this is very speculative, is how did life get on Earth? And we've had a couple conferences where we've talked about panspermia. And that's the thing that said that life doesn't arise on planets, it gets planted there from elsewhere. And this raises the issue,
let's put some biological information into those sails.
3.5 to 4 billion years ago, maybe some aliens planted life here. So it turns out we've started to do some thinking. I won't say we as the breakthrough initiatives, but maybe me personally. I just finished writing a paper with a couple other astrobiologists, Chris McKay from NASA Ames and Paul Davies from Arizona State, about how we might do that. And the idea is actually quite clever, that we could do this, in the next few decades, is that we now know that there are comets. These are little icy rocks in the outer solar system. That there's a number of comets that show up in our own solar system that come from interstellar space. The first one was Oumuamua that was actually discovered a few years ago. And in fact, the chairman of our advisory committee, Professor Avi Loeb at Harvard, thinks that it actually is an alien probe. He's probably wrong, but I won't say 100% wrong. But at any rate, that if you see one of these comets going through, you could go and plant what we call an inoculum in it, which would be a designed life form that when it goes through another star system and the ice begins to melt, these inoculum would be scattered to that star system, and they could, if there's a planet there that is suitable, they could begin to boot up life. Now, that has a lot of ethical and other questions, but you could redirect these comets slightly. So, they would take hundreds of thousands of years to go between stars, but, in the case of, billions of years, it doesn't matter. So there may be ways that in our own lifetimes that we may decide that we want to spread our life form elsewhere. Big argument, but I think we know how to do it now.
You've mentioned some contra-arguments.
Yes.
How do you deal with them? Because it has to be a lot of them.
Well, this is a key question. We're planning sometime this next year a conference to begin discussing these. probably at the University of Durham in the UK. There's been quite a lot of discussions about the ethics of spreading your life elsewhere, and especially if there may be unknown life there. Now, this is, interestingly enough, it's not just a ethical question, it's a theological and philosophical question. But this is one of the most fun things for a scientist or a philosopher to think about is you know, what are we here for? What's appropriate for us to do and not do? So it's, to me, it's one of the most fun things to think about is not only how did life get here, but, you know, should we spread it elsewhere? And like I said, it is a theological question. To me, some of the most interesting thinking was done by you know, religious ethicists. On my PhD committee, I had a Jesuit priest who was also later the director of the Vatican Observatory, and he used to raise these questions. We used to call him Father Photon, but you know, and I think this is a topic that may link, you know, philosophers, theologians, you know, scientists and ethicists. It's a fun area.
Maybe to these opinions and arguments, do you have any idea, or maybe specific ideas, where these technologies developed for this specific project, where we can use it, you know, on Earth? Like, where are the applications, maybe with these very powerful lasers or with these materials? Do you have some ideas where we can use it?
Very much so. I mean, it turns out that lasers are very exciting, and that's one of the reasons we had the discussions here. And there are both the strategy mission or questions, legal questions, and technology questions. But that lasers offer an incredibly powerful way to push things around our solar system. But maybe the most immediate thing is that we're worried now about debris orbiting the Earth. There's you know, as more and more people launch things, these things can hit other satellites. And one of the most promising ways to fix this is to use a very powerful laser on Earth to deorbit things. Now, the question is if you have that powerful of a laser, how do you make sure that it's not confused as a weapon or used as a weapon? Now, that's a challenge that I think that there are procedures and things. And our laser will be, you know, maybe 100 times even more powerful. So, so that's one of the big issues. On the other hand, that in addition to solving the debris problem, the laser, as powerful as we're looking at, can protect the Earth from, you know, we know that asteroids impact the Earth. You know, 65 million years ago, a big one wiped out the dinosaurs. Smaller ones occur all the time. These lasers are powerful enough to push them and push them out of the way. So it's an important technology that we need to look at, but we need to figure out how to do it safely and so in a transparent manner.
During your speech, you've mentioned the discovery of the first pulsar with the signal. Okay, we had some indications about the signal, maybe artificial signal from the Alpha Centauri system. And right now with the project, you're aiming to the Alpha Centauri system. How would change the maybe final location decisions change if we found really a great, strong signal from another system? There can be, you know, some intelligent civilization. Would the final destination change?
Well, maybe. You know, if it was up to me, yes. It depends how far away it is.
Okay, 40 light years away, 39.
Well, at the speed we would go, that means it would take, you know, 150, 200 years to get there. So it's, well, we can build a bigger array and send it faster. But you know, I would think that if we found a signal that we believe is real, then that's going to raise a very interesting set of questions. Do we answer? And if we answer, what do we say? Who's we? You know, I mean, you know, humanity isn't very united. So I imagine if we found this signal, the United Nations, you know, Outer Space Office would start convening meetings. In the meanwhile, other people may just decide to do something. But you know, I think that we'd have to examine carefully what we know about the signal we saw. Is there information in it? Are they trying to communicate with us, or was this an accidental signal? In the technosignature community, accidental signals are called leakage. They're leakage of their technology. So we'd have to figure out, were they trying to communicate with us, or was this just that we overheard their conversation with, you know, in some family? And but I think certainly if we find a evidence of an intelligent species, the first thing we would do is build really giant space telescopes to see if we can get more information. There is an idea that we've been working with some colleagues that it turns out that if you can get, you know, the distance to the Earth and the Sun is called an astronomical unit. If you can get 500 astronomical units out, which is about 4 times further than our, you know, any of our spacecraft have got to date. But if we can do that fast enough, and these, by the way, these sun divers I talked about can do that. If we get to a point where you can line the sun up with this other star system, the sun actually acts as a lens, it's called a gravitational lens, because by general relativity it bends the starlight. So it's a million-kilometer telescope, and that is got enough power. We could actually image that planet, and we could say, okay, what do we know about it? Is there cities on it? Is there other things? So the first thing I think we would do is probably, you know, start doing that, and then consider, should we send a probe there, even though it might take hundreds of years to get there. And you know, probably not in my lifetime. I'm 72, so I'd like to be around a few more decades, but I probably won't be around a few centuries. So. But a very exciting question. I hope we have that challenge.
I bet you've seen the movie. I hope it's the same in English, but in Czech it's called Contact with
yes.
Foster.
Yeah.
And, yeah. How realistic is the scenario?
Well, that's actually quite realistic. You know, the creator of that is Andruyan, and you know, she was on the stage of the picture I showed with Starshot, Carl Sagan's widow, and she's also the creator of the Cosmos series. And they did a very, very good job, and Carl Sagan was involved in that as well, of how we might find a signal, and you know, what the interaction would be. You know, now, you know, it becomes speculative that the aliens are trying to get us to build a wormhole or something that can get there. But I think that how the signal might be found and what would happen is pretty realistic.
If you have any other further questions, you can post it on the Facebook account Czech Space Portal, Český kosmický portál. We will follow like another 10 minutes, so you can have your own questions. Maybe from the audience right now over here, do you have any? We are in the Impact Hub in Prague, so if you have over here questions, maybe Andrzej. What thickness?
Thickness. That's a good question. Very, very thin. I think these things would be, you know, microns thick. So I don't know, a few microns. They're not very thick.
And what's the weight of the whole concept?
Well, that's an open question, but we'd like the entire system with the sail and the chips to be in the few grams, at most a few tens of grams. That's kind of the range, and a lot of it depends on, you know, there's trade-offs. You know, in one sense, can we build a bigger array? You know, if you want to have a bigger, and there are some of our experts that want us to build things that could send kilograms. Of course, and that ends up being, you know, 10 times bigger and so on. There are others that believe that, well, you don't have to go as fast, you can go slower, but generally you're talking about, you know, 5 or 10 grams for the entire system, the nanocraft, and you know, a few microns thick. So that's sort of what we're looking at right now. By the way, did I get that right? James Skulkfake is our program manager who's sitting over there. Is that right? Did I listen properly to the reviews?
Any other? I will go maybe.
I think right over.
Yeah, sorry, apologies.
That's an excellent question. Right now, the initial phases are going to be a few $100 million US dollars. Mr. Milner is committed up to $100 million. He's had discussions with other high net worth people so we think the initial research phase is probably to be funded by private, philanthropists. At that point, then the system, we're aiming for something that's comparable to the Large Hadron Collider or the James Webb Space Telescope. Those are sort of 10, 20 billion, dollars or euros, whatever you want to pick. That would have to be governments, and this is what it's called in the United States a public-private partnership. And in some sense, it's the way the United States, for example, does large astronomical telescopes. Right now, these new telescopes being built are built privately, but then they're turned over to the government to build a lot of the more expensive instruments and infrastructure and operate them. So we're looking at something similar to that. But the total cost is in the range that several governments might work together, just like the Large Hadron Collider was, I don't know, there are 10 or 15 different countries that contributed to that. And this would be the same thing, we think.
Mention it, James Webb. What are your expectations?
Well, I just hope it goes. I mean, this is a I guess it's a heart in the throat kind of moment when you're kind of like, oh my goodness, that's. I sure hope it works. It's a spectacular instrument. One of my concerns is that you put that much wealth and scientific community's promise on one launch. One of the things we are very interested in is, can we lower the cost of these telescopes? And I'm confident in the next few years that was a very large budget. Maybe we can do this for 50 times less expensive, because new technology is coming along quite well. Elon Musk has talked about putting telescopes in space for a lot cheaper.
On the moon.
On the moon, or even in space. That's
right now around 4,500 exoplanets, confirmed exoplanets. How many things are there?
Well, I don't know. The galaxy has, what, 10 billion stars? And, every star, every hundreds of billions, but every star probably has 5 or 10 planets. So, and probably a quarter of them have a planet the size of the Earth in the habitable zone. So, in our own galaxy alone, there's maybe 50 billion Earths. Potentially, and maybe a lot more. And, so my point is that I have learned never to think there's anything unique about yourself. And so it's very likely that there's life everywhere and there's intelligences everywhere. And we'll find them.
Carl Sagan said it would be waste of the room of space.
Well, if there is no life elsewhere, that's equally exciting and scary.
Yeah. It's like the no fish in the ocean.
Right. Well, as you mentioned the fish in the ocean, one of our advisors is I'm tracing at SETI Institute. Jill Tara, yes. Jill makes a statement about that all we've done to date is like dipping a cup of water in the ocean and looking at it and saying, well, there's no fish, so there's no fish in the ocean.
No fish. That's my evidence.
What she claims is that what we're doing is filling a hot tub, so at least there's more likely but we need to look a lot bigger. We need to fill at least a swimming pool.
Breakthrough Initiative, it's the private project, it's a completely private project. Why do you think this project is not led by space agencies? Because it's really breaking, and I know a lot of people who are saying that those break new step or giant leaps only agencies and public money can.
Well, we welcome money. Anybody wants to put any money in, and but we're seeing space agencies begin to pay attention to this. NASA, for example, now has a program to look at interstellar visits. They started it after we did. We like to think we encourage that. Technosignatures is an area that that when I was the director at NASA Ames, it was considered you couldn't even think about it. In the early 1990s, the U.S. Congress actually put a law in that we couldn't spend government money on. Fortunately, it was a one-year law, so it's ignored now. But we're now seeing both NASA and the U.S. National Science Foundation put money into techno-signatures. We're seeing a lot of other countries do that. There's a new radio telescope the Italian government has in Sardinia that actually has a major effort in this. A lot of these projects we're doing are joint. I mean, the project with China is very exciting. That with their new 500-meter, there's a major program to use that, which is the world's largest radio telescope for techno-signatures. So we're seeing more and more efforts by space agencies.
Let's get way closer back to Earth. Let's get to Mars. What's your guess? What's your human first steps on the Mars? Your guess? Because it's a very
2033.
2033, and who will be that? Like not the first person. Will be that a space agency or some private project?
Well, I think it'll end up being a public-private partnership. Right now, I'd say it's likely that SpaceX will do that in concert with NASA and maybe other space agencies. That this would be a mission that would have several space agencies involved with it, and at least SpaceX and maybe others. So I'd say 2033.
I have a last question, Ivo.
Well, excellent question. About 2 years ago, we had a major meeting at Hylace, and we had a meeting the last couple of days, and that was a very productive meeting. We're now seeing that Hylace has a space laser program they've started, which is, I think, very promising. And at the same time, we actually had a group of experts from the University of Trento, including the former head of the Italian Space Agency, that talking about working together. We also had some discussions with some of the strategy and legal people, how we put in the sort of legal framework for these kind of missions. So there's clearly significant laser expertise, as well as I think there's commitment to begin looking at using lasers in space. In fact, I'd say that that here is probably the lead thinking in the world on that.
Great. Thank you very
much.
Thank you. Thank you very much. Thank also you two in here in Impact Hub, also watching us on the Czech Space Portal Facebook. You can replay all the interview and also the whole speech of Pete Worden, who is right now in Prague, and maybe do some negotiations with Czech institutions about cooperation, about the great breakthrough projects, where we would like to know if there is some life in the other systems in the universe. Thank you very much. You were just watching some little discussion during the Czech Space Week, which is ending in these days. And thank you very much for you and for us.
Thank you.